Okay, here we are, last week of class. I want to talk about a chapter in a Stata book that I posted on week 10. It's a nice little summary of a lot of extensions, simple extensions of OLS regression that Stata can do very easily. Some other software programs can't do as easily. And they might be handy. Some of them are more important than others. And I want to organize them according to what impacts these adjustments have. I want to start out with a couple of things that affect the standard errors that you estimate, but not the coefficients themselves. And one of these is robust standard errors. You can ask for robust standard errors by just putting in comma robust at the end of your regression statement. The second one is clustered standard errors. These are very different. And to do that, you add a cluster and then put in some sort of identification number for the units that constitute the clustering units: schools, teachers, families, and so forth. Just an ID number. But so in both cases, these don't affect coefficients, but they do affect standard errors. Big deal, robust standard errors, not so much. Clustered standard errors in certain circumstances can be very important. And indeed, the whole HLM program was invented to handle this problem, but Stata does it with a slightly different adjustment, but it amounts to the same thing actually. So let's talk first about robust standard errors. When you look at the standard OLS regression estimator, it makes a lot of assumptions about the nature of the data. One is that the variance of the scatter is fairly even across the distribution of X. All right, this is one of the things that offended statisticians with a linear probability model, and that's why they invented a logit or a probit transformation. Part of it was to avoid predictions outside the 0-1 range, and part of it was to better address this this non-standard variance, this heteroscedasticity. We've talked about that before. So heteroscedasticity would be a case where there was a portion of this X distribution where the variance of the observations was much larger at certain portions of X than others. So how do we deal with this? Well, it turns out there's a very simple way to deal with it. And that is to ask Stata to estimate robust standard errors with this comma robust command. And it will, I don't want to get into the details here, but it will adjust for this non-uniform variation around the regression line. And it will have some adjustment, not very much of an adjustment to the standard errors. Doesn't affect the coefficients, right? The slope of this line isn't affected. Is it a big deal? Not really. The adjustments are pretty small. More important is addressing the problem of clustered standard errors, right? So not only does the OLS model assume, let's take away these offending observations here. Not only does the OLS model assume that there's this homoscedasticity, there's this constant variance as you go up and down the level of X, but it also assumes that every observation is independent of every other observation. So let's say you were taking a representative sample from the US population, and you went out and took every 1 millionth person in the United States. There are what, 330 million, so you'd have 333 observations. If you took them totally at random, then there would be no reason to think that one particular observation was independent, was not independent of any other observation. But think about the ECLSK, right? ECLSK went in and sampled kindergarten classrooms. And then as a second stage, it selected a small number of children within each of those kindergarten classrooms. So those kids are more alike than two kindergartners drawn at random from the population as a whole, right? The kind of characteristics that lead kids to end up in the same kindergarten classroom lead them to be probably more alike in many other ways as well. So, you know, we have talked about fixed effects. This is different. This is all about non-independence of observations, and we'd like to be able to adjust for the fact that we've got non-independent observations. And again, there's an easy way to do that. One way is with an HLM model, a multi-level model, where you've got kids at the first level and then classrooms at the next level. That automatically adjusts for the non-independence of kids within classrooms. But there's a pretty straightforward way in Stata as well. And that is to use cluster, where you're clustering the standard errors. And what it does, I'm teaching you all these big words, heteroscedasticity. How about Huber-White sandwich estimator? Try that one out on your friends and see if you get an ooh and an ah. So again, I don't want to get into the details here, but you're telling it to look for possible non-independence within the ID categories, right? And if this is, in the case of the ECLSK, you want classroom ID. So one distinguishing ID number for every classroom. You feed that to Stata, and it will look to see to what extent the kids who are in the same classroom are less independent of one another than kids just at random from the population of kids in the ECLSK. And it makes an adjustment. So let me erase this, as does HLM. And this can be a big deal. If in fact you've got a heavily clustered sample, and the clustering is such that people within a particular cluster are really a lot more alike than people who aren't in that cluster, then you can get some pretty substantial, in this case, increases in your standard errors, because if you don't do something like this, you're really assuming that all these observations are independent of one another, but they're not. So you really have fewer effective degrees of freedom than if they were completely independent of one another. So that's going to increase the standard errors, and sometimes substantially. This is also something you can do if you've got a sample of siblings in the same family. Again, we talked about family fixed effects. That's different. That's going to affect coefficients. It's not going to affect standard errors. But if you have a data set, the panel study of income dynamics is an example. You know, that data set that we used in the very first example in the first class, where we looked at the relationship between childhood poverty and completed schooling. We took, when we did that article, we took all kids observed in the PSID between birth and age 15, and then observed actually to age 22 or so, where we got completed schooling. But if there were a couple of kids in the same family, we took both of those kids. So in that case, you had clustering within family. And there's a lot of reason to expect that kids who are siblings in the same family are more alike than two kids drawn at random from the population. So clustering on family ID is going to make, can make a quite substantial adjustment to the standard errors. Again, it's not changing coefficients, but it is changing standard errors. All right, so this is kind of a no-brainer. If you've got a clustered sample, it's easy to make the cluster adjustment. One thing I might point out where this option comes in handy is suppose you've got a data set where you observe the same children at multiple points in time. Let's say ECLSK, let's say ECLSK kids in kindergarten and first grade. All right, and let's say you're just interested in a correlation between executive function and achievement, math achievement or reading achievement. And let's say it's okay to have a cross-sectional correlation for this. Executive function is not well measured in the ECLSK data set that you're using for the lab, but in the more recent ECLSK, it is, there is a much nicer set of executive function measures. So let's say you're using the more recent one, you've got executive function measured for these kids in kindergarten, let's say 5,000 kids in kindergarten. Those same kids are followed into first grade. Again, you measure executive function and you measure achievement. What did I say, 5,000. Now, if you just want to estimate a cross-sectional relationship, you've got 10,000 kids with observations on executive function and achievement in the same year, right? You've got 5,000 kids in kindergarten, and you've got those same 5,000 kids in first grade. So let's say that you were estimating achievement is some function of executive function plus controls. All right, and this is these are measured at the same time. We're usually saying it's not so telling to estimate a cross-sectional regression, but let's just suppose that it is in this case. So what you can do with this data set, with these data and this particular model, is estimate this for a pooled sample of 10,000 kids. It's the same 5,000 kids in kindergarten as in first grade, but for the purposes of estimating this cross-sectional equation, you've got 10,000 kids, right? Every kid has 2 observations. And you might want to add, let's say, B3 whether a 1-0 variable, whether first grade. Right, so a dummy variable to distinguish whether it's first grade or not. But this is obviously a case where you've got non-independent observations, right? It's the same kids in kindergarten and first grade, but they aren't identical kids, right? Children in first grade can look rather different from those same children in kindergarten. So if you want to take advantage of up to 10,000 observations, but also want to make sure that you account for the fact that they're not independent of one another, you can use this cluster adjustment for the standard errors, right? Pool the two grades together, create a data set of 10,000 kids, estimate this model, and then put in cluster and put in a child ID here, right? And what state is going to do is see to what extent the two observations for the same child ID are more similar than two observations from kids drawn at random from the sample. And they might be so similar that you effectively have only 5,000 degrees of freedom. It'll increase your standard errors accordingly. But what usually happens is there's a surprising amount of independence between a given child in kindergarten and a given child in first grade. So you make this adjustment and it increases the standard errors a bit, but you might effectively end up with 7,000 or 8,000 degrees of freedom to estimate this relationship. So this cluster adjustment, either in HLM, you can do the same thing in HLM, either in HLM or with this simple cluster addition to the regression command will enable you to do something like this. Okay, let me set up the board for the next. Okay, so new board, new topic. First, we talked about adjustments that are going to clean up standard errors. Now we're going to look at adjustments that can affect the coefficients themselves, which in some ways are are more important. So I say here, all of these both address outlier influence and they affect coefficients and maybe standard errors, but the fact that they affects the coefficients themselves are more important than their effect on standard errors. Two techniques here. One is robust regression, and the other is quantile regression, which ends up having other uses as well also. So what's the problem with outliers? Again, typically OLS is assuming homoscedasticity, a constant variance. And we've talked earlier about the potential influence of outliers, especially outliers that are at the extremes of the independent variable. So remember when in the second, I think, lecture, we talked about the formula for a OLS coefficient, and it was -2, and it was with 5 time points, -2 times what's over here, -1, 0, +1, +2 over here. The observations on the outside, either very low X or very high X, are getting much more weight when you run a OLS regression than the outliers in the middle of the X distribution. And remember, when you have this -2, -1, 0, +1, +2 set of values for X, what was in the zero, the time 0, could have been an incredibly high value of Y, a very extreme outlier, but it's going to have absolutely no effect on the slope because it's going to affect the height. It's going to pull up the height of the regression. But if it's right in the middle of this line, it's not going to tip the balance of that line. So we're not going to worry about outliers that are associated with middle values of X. But for values of y that are quite different from the best fitting regression line, remember OLS is trying to minimize sum of squared deviations of every observation from the regression line. And it's a least squares criterion, right? So this distance, in terms of its influence in calculating the regression coefficient, B, that distance is squared, right? That's how the least squares formula works. So you can see if you have an outlier out here, if you have an outlier down here, you get that deviation and you square it, it has the potential for influencing quite a bit what the slope of this regression is, right? And in some sense, if that outlier is real, maybe that should be the true slope, because you want to take into account you've got some very high values of y over at the extreme of x. But typically, that's not the case. We want to know what the slope of this regression line is through the heart of the data. We don't want a few outliers to heavily influence what this slope is. So people go through a lot of different kind of potential procedures to deal with outliers. There are diagnostics to look for them. When people find them, they might trim the outlier value down. Sometimes people start out by looking at the distribution of y, and if there are very extreme values of y, sometimes you truncate the value of that extreme y down to the 90th percentile, 95th percentile, or maybe the 99th percentile of the y distribution. Maybe you throw it out. That's what people do sometimes. But trimming it back in developmental psychology is called Windsorizing. And it's one way of dealing with outliers. It's a bit arbitrary, but it's useful. It's very important, actually, if you have a data set that you're not familiar with, to first take a look at the distribution of y and see what it looks like. See if it's reasonably normal. See if there are some cases that are sticking out like a sore thumb, either very large or very small, because if there are, and they happen to be associated with either very high or very low values of x, then they could really affect your coefficient estimate. So we'd like to be able to do something about that. We can do the Windsorizing, we can throw them out, but there are a couple of other techniques in Stata that you can draw upon. One is robust regression. So 10 minutes ago, we talked about robust standard errors. That's for standard errors. This is robust regression. It's a separate regression procedure, RReg. And what it does is estimate not with straight up OLS, but with a more sophisticated algorithm that gives an OLS type estimate, coefficient, standard errors, everything like that, but adjusting for potential outlier influence. And anything that it detects as being quite influential as an outlier, it ends up weighting down that observation relative to observations that aren't extreme. All right, so it's just another way of addressing this outlier problem. And you would hope that if you run a regression in the normal kind of way and run an RReg on the same variables, that it wouldn't make any difference, right? If it does, it's suggesting that there are some outliers that the RReg is taking into account and reducing their importance relative to just the straight up regression. So there are various ways of addressing this outlier problem. RReg is a nice way to do it. All right, so another possible way to do it, this is rather different. is to use quantile regression, QReg. And what quantile regression does is get a best fitting line. If you think about what OLS does, it's really based on mean Y and trying to get a good regression coefficient that based on the means. What quantile regression does is focused not on the means, but the medians, right? And if you think about it, a mean value of Y can be heavily influenced by an outlier, right? If you have a big value of Y, it could pull up the mean quite a bit. If you've got median criteria, you're not going to be affected. The median isn't going to be affected at all by whether this observation is here or here or here, right? The median is the 50th percentile, and the 50th percentile value isn't going to be affected by the outliers at either end. So a quantile regression fits to the median instead of the mean of these distributions. It too, therefore, is less sensitive to outliers. In effect, what it does is not take a squared distance here, but rather an absolute distance instead of a squared distance. So it reduces the influence that kind of way. And it gives you coefficients, standard errors, and everything. The robust regression is probably the first thing to turn to. But quantile regression can be interesting if there's some reason that you want to fit to the median of the distribution instead of the mean. But another feature of quantile regression is that you can fit this to the median of the Y distribution. But you can also fit to the 10th percentile of the Y distribution, the 25th percentile, the 75th percentile, and so forth. So what does that mean? Suppose you've got some kind of school-based intervention, and you want to know whether it's affecting achievement. So achievement is some function of the intervention. This is a 1-0, whether they're in the treatment group versus control group, plus controls. Right, and you run the OLS and it gives you a least squares criterion fitting for B1. You could run a median regression with QReg, and it would give you an estimate of impact fit to the median of the Y distribution. Or there's a way of saying, well, tell me what the impact of this regression is on very low achievers, right? On the 10th percentile of achievers. High achievers, the 75th percentile of achievers, the 90th percentile of achievers. You can specify whatever point in the percentile distribution you want. And indeed, it's sometimes useful to have a OLS, suppose this is 0.20, 0.05. So if standard deviation units, this intervention has a fifth of a standard deviation impact at the mean of the distribution. The median might be similar, 0.22, 0.06, something like that. But then you can march along and say, well, what about the 10th percentile? What about the 90th percentile? right? And it could be that your impact is particularly large at the bottom end of the distribution relative to the top end of the distribution, right? Or these could be reversed. You could have an intervention that was much more effective toward the top end of the achievement distribution than the bottom end of the achievement distribution. So it doesn't routinely happen that people turn to quantile regression, but it's useful to know that it's there and it's easy to implement in Stata, because in some cases you do want to examine what the distribution of impacts look like all along the distribution of your dependent variable. All right, let me set up the next board. Okay, let me continue here. Again, these are all in this Stata chapter that I linked to in the syllabus. And these aren't organized in any sort of grouping like the others, but I just want to point them out. I mean, you already know about fixed effect regression. You could add a bunch of dummy variables to a regression to get fixed effects. You can also do it with the procedure xtreg, where you specify what the fixed effect unit is. But you already know about that. So let's keep going. Stata allows you to estimate a constrained regression. Now, let's say that you're relating some outcome to math achievement and reading achievement plus a bunch of controls. And furthermore, let's say for some reason, you want to constrain these two coefficients to be identical, and then get a best fitting model with this constraint that B1 equals B2. So you can do that with a constrained regression, CNS reg, where preceding the CNS reg command, you specify what you want to constrain. In this case, math coefficient equals reading coefficient, and it will run the regression, get the best fitting line, taking into account this constraint that those two coefficients have to be the same. A more common problem that you might face is when you've got a truncated dependent variable. So by truncated, we mean that let's say we're looking at years of education as a function of wealth, family wealth. And let's suppose that the data set that you have is measuring family wealth pretty well down to 0, but it's not taking on any values where people are in debt, right? Where their net worth is negative, where they have more debts than assets. So your distribution of wealth is truncated then at 0. So I'm sorry. So let's just look at a frequency distribution here. Forget about a relationship with those variables. Frequency distribution. There might be something that looks like that. Median wealth is maybe $50,000, let's say. Most wealth people have is in the form of the equity they have in their home. And then you've got a long tail, obviously, where there are very, very wealthy people And then you've got a distribution of wealth that's less than 50,000. And if you had a full measurement of wealth, you'd have not only going down to zero, but you'd have negative wealth values as well, right? People whose assets are less than their debts. They have negative net worth. But we're supposing in the data that you have this truncation point. So you've got points along here, but you've got this very heavy concentration of zeros that are reflecting all of the observations, not only at zero, but for negative values of wealth. So you'd like to have a nice, well-behaved distribution for your independent variable or dependent variable here. This is a dependent variable. But your data constrains you from observing negative values. So what do? That's a situation where if wealth with the dependent variable is truncated, and there's a procedure, Tobit. Actually, there are a couple of procedures, but Tobit is a regression procedure where you specify the truncation point, zero in this case, and then it runs what amounts to an OLS type regression. So sometimes you'll encounter these truncated variables, and Tobit is a useful approach to that. Finally, there is a procedure when you know certain independent variables, let's say, are measured with error. You know, typically this is a situation for SEM where the measurement error is kind of incorporated into the estimation. Didn't really have time to develop this, but measurement error in X variables often bias coefficients on X towards zero. All right, so this is a biasing problem, and that's, you should learn to fear when you get biased estimates, and measurement error is a potential cause of bias. So it'd be nice to somehow adjust for the bias that results from the fact that you know the X variable has a certain amount of measurement error in it. And there's this procedure, errors in variables regression, EIV reg, where you specify the reliability of X1, X2, etc. And EIV reg runs the regression taking that into account. So you haven't worried about this up until now, right? And up until now, when you just run your regular regression, you're implicitly assuming that all of your X variables are measured with no error whatsoever, right? And the coefficients are being delivered to you under that assumption. But in some cases, you've got X variables, maybe they're scales of some sort, and you know from the literature exactly what the reliability is for those measures. So if that's the case, and they're important X variables, then you can specify in the regression command, the EIV reg command, exactly what the reliability for each variable is, right? Assume that the reliability of X1 is 0.85, the reliability of X2 is 0.9, and so forth. And it will give you what amounts to an OLS type regression, coefficient standard errors, that take into account that unreliability, right? And usually when you compare it to a regular OLS, where you assume there's no measurement error, there's perfect reliability, you'll get an increase in coefficients because you're no longer getting this downward bias for measurement error because you're adjusting for the measurement error. All right, so there are a couple more of these kind of procedures that Stata can do that are explained in this chapter. It's useful to know what the possibilities are, because a lot of times for a particular problem, you just you know that you're not it's not kosher to do an OLS regression, and you really don't know what to do to get around the particular problem that's making it not kosher. So here's a variety of techniques, one of which may do the trick. And they're all explained pretty well. They're easy to implement in Stata. So important to know, and you might want to try them out.